This is your last video in Chapter 7. I'm looking at 7.5 Day 3 notes. And 7.5 Day 3 is going to introduce a new type of growth model that you've never really encountered before. So because of pre-cal, you should be very familiar with exponential growth and exponential decay, and basically those are both using the PERT equation. But you and I both know that there are some instances where exponential growth cannot go on indefinitely. Like if you're looking at population growth, you know that the population cannot just continue to grow exponentially. The population will start to level off at some point. Start to. I'm not saying it completely does, but it's gonna reach a certain point where it's gonna start leveling off. So, compared to exponential growth, where in exponential growth, notice if you look at the derivative of exponential growth, if you look at like the slope of the tangent for exponential growth, the tangent line just gets steeper and steeper and steeper and steeper, and the slope of an exponential function approaches infinity. So, as we know, that exponential growth cannot continue indefinitely in many cases. So what we're going to do is we're going to look at logistic growth. Well, logistic growth starts off growing exponentially, and then the growth still growing, but it's slowing down, it's slowing down, it's slowing down because it's starting to level off. And so what's going to happen here is there will be a value that this function is headed toward, okay? And we call this value that the function is headed toward, it's called the carrying capacity. Carrying capacity. So it starts off growing exponentially, and then it starts to slow down, slow down. So check out the slope of this function. Because really, we're going to be just as concerned about the slope of the function as we are going to be about the function itself. So the slope of the function starts off to be pretty close to 0. And then it gets pretty steep, 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 steep. I think right around here is where it's the steepest. So the slope would be the greatest. And then slope decreases, decreases, and the slope of the function, the growth rate of whatever this is measuring, the rate of change is approaching 0. So the rate of change down here was approximately 0. That didn't last long. Slope, rate of change, increasing, increasing. Highest rate right around here. Rate was getting lower, lower, lower. Rate of change is approaching 0 as this function, this y value, approaches the carrying capacity. Okay, so we're going to largely be talking about population today. So I'm going to say that the y-axis measures population. The x-axis measures time. Okay. And this function would be, I'm going to call it P of t. If it measures population, why not name it capital P, right? Okay. So, it's kind of wordy over here, but it's all good. It's really all good stuff. Notice that if you look at exponential growth, like PERT, your derivative, notice what happens to your derivative That's supposed to be an equal sign. dp dt equals k times p. Oh, I just now caught that. All right. So if we're looking at exponential growth, remember that you have your derivative is just some constant times your original population equation or whatever. So you know that if you look at exponential growth, your slope of your function, your derivative, can get out of hand. This can get out of hand because the slope of an exponential curve just keeps increasing and increasing and increasing. So what logistic growth does is it takes that slope. I'm down here now in the logistic part. So it takes the derivative, it takes that slope, and it puts this thing on it called a limiting factor. So as the slope takes off, increasing slope, increasing slope, increasing slope, the limiting factor is going to kick in and say, whoa, slope, hold up a minute. Don't go so fast. And it limits that slope. So it takes the slope, which in an exponential function is going to do this. The limiting factor does this to it. Whoa, slow down, slope. Slope, I want you to get close to 0. That's what the limiting factor does. Now, the limiting factor is the okay, and something I forgot to tell you. Carrying capacity, we use capital M to represent carrying capacity. So keep in mind, if this is a population curve, the y value of my population, or the p value if you want to call it, the p value of my population is getting close to capital M, the carrying capacity. So check out what this limiting factor does. Remember, this represents the slope of that curve. And if the curve just keeps growing exponentially, the slope is going to get out of hand. So the limiting factor is my carrying capacity minus the actual population. Carrying capacity minus the population. Well, at the beginning, that's a big difference. Carrying capacity minus actual population, that's a big difference. But as the slope starts changing, getting out of hand, we need that limiting factor to say, whoa, slope, hold up. So changing the slope changes the function. So as we go out here, the limiting factor, m minus p, begins to become a very small number. So what's happening is this slope, the derivative, the slope that's getting out of hand, gets multiplied by a very small number, which limits it. So it doesn't get out of hand. And again, remember, this is all about, this is like a logistic growth derivative. This is telling us about the slope of a logistic curve, okay? I hope I explained it well. If we were in class, I really would like you all to answer these questions. So I think what I want you to do is maybe pause the video and see if you can answer the questions by yourself. That'll get you such a better understanding of the logistic growth model than if I just answer them all for you. Try it, see how it works. Okay, so I'm looking at number 1, and we're looking at the logistic one, when will the slope be close to 0? Now, the question is about this equation. This is the slope of a logistic curve. This graph is the logistic curve. So, number 1 says, when will the slope be close to 0? Actually, do it without looking at the graph first. When will this be close to 0? This is going to have a value close to 0 when Either my population is close to 0, or when this quantity is close to 0. So when these two get to be close to each other. So I can answer this by saying, where is it? When P is close to 0, and when P is close to M. Okay, number 2. This is kind of cool. Really hoped you hung on to this until you understood it. This is, okay, it's calling it y, but I really wish it hadn't done that. It's just wanting you to know that it's a function. It's really the derivative. So maybe we can look at this as dy dx. But if you take dy dx right here and you distribute the kp, dy dx equals kpm minus kp squared. So this actual function, I know it represents the slope, but this one, if we graphed the derivative, it's an upside down parabola. What's the value of p at the vertex? Well, you would use your vertex formula. You would go p equals the opposite of b over 2a. So you would use the opposite of b over 2 times a sorry, I forgot to put the opposite there. The opposite of b over 2 times a. My negative k is canceled, and I get capital M over 2. That's the carrying capacity cut in half. That's where the vertex of this parabola would be. Now, use this, the answer in number 2. Why is the growth rate slope maximized when the population reaches half of the carrying capacity? Why is the slope maximized? Why is the slope maximized when this graph reaches half of the carrying capacity? Well, because where is slope the steepest? Slope is the steepest right here. What's the value of p right there? The value of p right there is half of the carrying capacity. Once the population reaches its halfway mark, that's when it's growing the fastest. I guess I can answer that. Because p prime, the slope, upside down parabola, looks like that. Okay. If the initial population is less than m, as is pictured, the initial growth rate would have to be positive. If the initial population is greater than m, well, that's not what's pictured, but that could be the case where the population is decreasing, but it's going to level off as well. So then the initial growth rate there would be negative. If the initial population equals the carrying capacity, if the initial population equals the carrying capacity, what's the initial slope going to be? 0. And as t approaches infinity, where is p headed? As t approaches infinity, where is p headed? P is headed toward m, the carrying capacity. And no, it doesn't matter where it started. It doesn't matter what the initial population was. Okay, we're going to do the two problems on the back. I can tell you that we are going to end this chapter with a bang. Example 4 is not going to be too bad. Get you an extra sheet of paper for number 5. It's going to take a bit. Number 4. So number 4, this is the derivative of the logistic growth model. And so according to the way it's set up, this is K. So it looks like right off the bat, I can tell that my growth rate is 0.08%. Okay, population. Carrying capacity is 100. Oh, I just answered the first question. Haha. Carrying capacity, 100. Part B. What is the bear population when the population is growing the fastest? Okay, well remember, it's growing the fastest. The slope is greatest, so it's growing the fastest when it reaches half of its carrying capacity. What is the rate of change of the population? So this is asking us, what is the rate of change? It's saying find dp dt when the population is 50. I'm going to take the equation that they gave me, 0.0008. Oh, hang on, let me use proper notation here. Evaluated when P is 50. My bad. Okay. When P is 50, I got 20 out of that. And let's put a rate on there. It's asking for a rate. Find the rate of change. So this should be 20 something per something. So let's see. This is population growth for bears. T is measured in years. So it's bears per year. There you go. Okay, now to this one. The equation is not that much more difficult than the equation at the top. It's what we're supposed to do with it that makes it harder. So I'm looking at this and I'm seeing, okay, the original equation is P for population of something, moose. Okay, moose population. Looks like the carrying capacity is 1,000. The growth rate, this is K right here, so the growth rate is 0.03%. So part A, carrying capacity, that is easy. We can do that. That is 1,000. I don't think any of us have a graphing calculator that generates a slope field. I know none of mine do. And the best I have is the TI-84 color backlit edition. And I don't think mine does that. Okay, here we go. Part C. This is what's going to take us so long. Solve the differential equation. So what we're going to do, we're going to get a general solution. We're going to do some work, quite a bit of work. We're going to get P equals, it's going to be a general solution. It's going to have a C in it. And then we're going to sub in that initial condition. to figure out what c is, get our final equation, circle it, and praise the Lord when we're done. All right, here I go. This looks like a problem where I use separation of variables, right? So if this were in terms of t, it wouldn't be that bad because t is my variable. This is in terms of p. That makes it difficult because p is actually the name of the function that I don't know what it is. That's what I'm trying to figure out. So I need to get all my p terms over on this side. I'm going to get all of my t terms over on this side. So obviously, I'm going to divide by p times this quantity. Now the question is, do you want to keep the yucky decimal over here where the t is going to be, or do you want to put it over there where the p is going to be? I'm going to keep this over on the t side, and I'll tell you why in just a minute. It would help if I wrote it correctly. Whew, hope y'all don't do that. Okay, so there were only 1, 2, 3. My bad. There were only 3 zeros, making this worse than it actually is. And I'm going to integrate both sides. Doing this integration, t is my variable. This is going to be easy. I'm just going to throw a t on this decimal. If this were over here, you would take a kind of complicated antiderivative and you would complicate it even more by having 0.0003 up here, and you would want to move it to the front. It would, so first hint at getting through these problems without wanting to kill yourself is make a star so you know, keep the yucky decimal on the t side. It's going to save you some headache later, okay? Now, to do the antiderivative of this, this p and this quantity are linear factors. That means you're going to have to do some partial fractions. So I think what I'm going to do is, since you all have got an extra piece of paper, I'm going to take this and work on it up here. Okay, so I've got my partial fractions set up. So I need the parentheses on that one, and I need an extra p on that one. And once I get that, we're going to focus on the numerator. So I've got 1 equals a times the parentheses that I needed plus b times the p that I needed. find A, I can let P equal 1,000. One, two, three. To find B, I can let P, no, to find A, I can let P equals 0. I think they're both that value. Okay. There we go. So if I move, I'm considering separating these two, but I'm not actually showing it on my paper. So I would move this out to the front, and the antiderivative here would be natural log of P. Next one, move this out to the front, get it out of the way. This would be natural log of P, but the P is negative. So remember, if I had you do the whole U substitution thing, you would have to balance that out by putting a negative in the front. So this one turns out to be minus 0.001 ln 1,000 minus P equals 0.0003 T plus C. Now, I'm not really sure why this happens, and maybe I'll realize it once we get farther in, but a couple things I know. I know that both of these logarithms have a 0.001 on them. I'm going to pull that off and undistribute it. I also know that I'm able to condense these. Oh, I know why. I'm able to condense these into one logarithm. So but time out. Here's the thing. When I condense these, this one's going to be on the bottom. I don't want that to happen. I don't want the binomial with the P in it to be on the bottom. And I'll tell you why when we get there. So if I don't want this on the bottom, then I think what I want to do is pull out the negative and flip them around. Okay, so next thing I'm going to do I'm going to do two things in one step. I'm going to divide both sides by negative 0.001, and I'm going to condense these down to one logarithm. And just to make sure I don't do something stupid with decimals, because I have been known to do that. That is negative 0.3. Okay. Now, I still haven't told you why I wanted you to flip these around, and I understand. I'm not going to tell you that just yet. Just trust me. In fact, this is the next, let's see, I had you star up here something to do so that you would get through the problem without crying. That's your next star. Put a star around like here-ish to make sure that when you have two logarithms, when you get ready to condense them, you want the monomial to be on the bottom. You'll see why in a minute. Okay, now, I am so sick of writing these absolute value symbols, I want to get rid of them. Can we? So, think about this. Population. I've got it in absolute value symbols. Will the population ever be negative? Well, at the beginning, the population was 61. So I think that's a no. The population's never going to be negative. What else has absolute value? What about 1,000 minus the population? No, that's not going to be negative. That's a carrying capacity. The carrying capacity minus the population. Remember, this limiting factor makes the slope approach 0, so the population isn't going to get there. I can drop those negative symbols. So I think I will. In my next step. And in my next step, I'm going to say, you know what? I need to get these out of a logarithm, so I'm going to do my e to the thing. And I have e to the, so the natural log cancels out. I've got 1,000 minus p over p is equal to e to the negative 0.3t plus c. Oh, that's just e to this times e to c, so the constant gets moved out into the front. So that's just a constant times e to the negative 0.3t. Holy moly. And now we got to solve for p. P is in two places. It's in the denominator and the numerator. So what you're going to have to do is you're going to have to multiply both sides by p. Get all your p's on one side, everything else on the other. Factor out a p. And divide. Holy moly. But that's it. Well, that's not all of it, but that's the general solution because it has a C in it. It's the general solution. That's the family of functions. That's the huge possibilities of the original P function. Now, last thing, way back up here at the beginning of the problem, it said solve it. We kind of did, but now let's use that initial condition to figure out what C is. Well, it can't be much worse than what we just did. So plug in 0 for X, or T, plug in 0 for T and 61 for P. 61 for P. E to the 0 is 1, C plus 1, yep.